started again. They rang the bell early for the last talk and a little bit late for this one, so averaging out to start right. I'd like to introduce Ryan, who's our today's motivational speaker, and he's going to be speaking about coalescence and RX.
Thank you very much, and thank you very much for inviting me. And sorry I was very late with both title and summary. I had hoped to have some material in that we didn't get to that. That's why the reason of my delay. The reason for this talk is motivated by reconstructing the evolutionary process and the history of sequences, because it's not going to be very practical, but that is the sort of motivation that if we study this problem hard, it will contribute to this. And I'm very keen to understand why these problems involving the ancestral recombination graph is an inherently hard problem. It's easy to say it's hard, but there's a lot of ways of characterizing how hard it is. The actual talk will have something on the coalescence with recombination, bounds on recombinations in a data set, what's the minimal number of recombination we need when you have a set of sequences. Then I will, we have two algorithms for this, one that scans sequences and one that goes back in time. And I couldn't help sort of discussing a couple of other problems in bioinformatics that have the same property, that you can find two sets of algorithms that solves the problem. And lastly, I will discuss likelihood calculations on what we call the epsilon arc, which is a subgraph of the arc that contains most of the probability mass. And please ask, I can be a bit jumpy in my presentation, so if I suddenly skip something, concept, please stop me. The basic evolutionary event that we can have for a set of sequences, if you view them back in time, is a coalescence. So two sequences find a common ancestor, or if you view it forward in time, they duplicate. The other event, basically three basic events, is a mutation. You have a sequence that begins present by line. A mutation will happen, and here's presented by a blue ball. And almost everywhere in this talk, and many populations, genetic context, we would have this assumption called the infinite site assumption. This basically means that the sequence is represented by the real line, and any mutation will always happen in a new spot. That is very convenient, because it basically means that every time you view a column in alignment, you can identify, you will only see two states, and this two states will define a bipartition of the tree on the tree. Recombination is this. If you go back in time, it basically means that this sequence has ancestral material, one part on this sequence, one part on this sequence. And as actually a physical thing, if you go forward in time, it means that this sequence and this sequence has met and swapped material. And when you label it backwards in time, which you do because you observe the sequence in the present, it has this sort of special configuration. There's a fourth event that we don't care about here, but it's also of interest, and many of the things I address here has also been addressed with this kind of event in the history of the sequences. Okay, so if we take a set of sequences in a population, so we have a big population with one individual up to big N individuals, we will basically sample a set of sequences. And what we do is that we go back in time, and we can encounter the events. So if we take this sequence here, could be chromosome 1, it found a common ancestor there. If we trace this sequence back in time, at this point in time, this sequence was created by recombination, and as illustrated on the previous slide, this one was created by a crossover between the sequence in the ancestral individual to this one and this one. So it has one history for this segment, another history for this segment. One can go further back in time and ask, when is this history finished? We have a root for a tree. It's finished from the point of reconstruction when all positions, when we scan along the sequence, have found one common ancestor. That's not a root, because proper root in any tree sense, because they can be spread out on many individuals. However, one can prove, as Bob Griffith did, that if you wait long enough, there's going to be one ancestor that is this sequence that carries the ancestral material of everybody under the standard coalescence recombination model. The first people who tried to look at a set of data set and say how many recombinations is in this data set was in 1985, at least a publication by Hudson and Kaplan. And what they looked at was Martin Kreitmann's data set from 1983. That was 3,200 long and had 11 sequences. And since we had this infinite site assumption of in operation, we will only observe 2 states in any column, so we might just well encode that with zeros and ones. And we can also, by taking an outgroup, assume that the zeros are the ancestral sequence if we want. The total sequence was 3,200. If you only cared about position where there was variation, you were down to 43 positions instead. If you only cared about positions where there were created non-trivial bipartitions, so i.e. groupings were always larger than 2 or larger, not 1 versus the rest, you will only have 28 sites. So this is sort of the motivational data set for this talk. What they cared about is how do you find a recombination? Well, you can look at this one, this column here, and you can look at that column there, and you can then find out that they cannot be placed on the same phylogeny. And since you are not allowed to have multiple events, you must declare a recombination between this position and this position. For instance, you have the same situation here. If you look at this column and this column, there must be a recombination event between these two. Without too many further considerations, and if one wants to be efficient in the use of explanatory recombinations, one would postulate a single recombination there because that will explain this and will explain this. The motivation for their investigation of this was a paper from 1975, without doubt, by Geoffrey Watterson, that did a similar thing for mutations. And basically, what did Watterson do? There's no recombination. Is that you observe some sequences here, and then you find out. Then you do the same thing with the data as this. So you basically count how many columns there are variation. And if you have the infinite site model, every time you have a mutation, it's something that happens on a branch, and you can see it without a problem because it creates a bipartition. So you can basically take the data under this model and count the number of mutations. You can, in the coalescent model, calculate what the size of the total branch length of the tree. And when you have these two quantities, you can have an estimator that estimates what is the mutational rate per unit time. And that gave a decent mutational estimator for this parameter. And the idea was clearly to do the same. Take the data set there and try to observe recombination. Clearly, we observed a recombination between these two positions. However, as they also found out in 1985, this observing recombination is a much more complicated issue than observing mutations. Okay. But if one could do this, one would actually be in the same situation that we would not have a tree over it, but we have an ancestral recombination graph. But we could calculate the total length on the branches of this ancestral recombination graph, and if we could observe the recombinations, we have a recombination estimator. This whole endeavor proved much more difficult than originally anticipated. If we do, as we just did, take a set of sequences, we can encode it like this, and if we have a situation that if we have 4 sequences, we observe all 4 types. So we observe 0, 0, 1, 0, 1, 0, 1, 1. There must be a recombination event, and that's how you define if there is whether this column is incompatible with this column. This bound, which is you get a bound says that you basically only observe 8 nucleotides. You have a column there with 4, have a column there with 4. So you observe 8 nucleotides, and you conclude that there is one recombination event. This was strengthened by Myers and Griffiths in 2001 that allowed you to say the number of recombinations in a sample will obey this inequality. And it's actually very simple because basically you observe a number of haplotypes, and that's a number of sequences, small sequences. And what can create haplotypes is there must have been an ancestral haplotype. Every recombination could create one new haplotype, and every mutation could create a new one haplotype. So we have a very large number of haplotypes. You can easily observe the mutations because that's just the column of the variation. But if you have a large number of haplotypes, you will get a stronger bound for how many recombinations there is in the sample. So that's 2 local statements about the number of recombinations that you can find in a sample. Clearly, what you're after, and also what Hudson and Kaplan was after in the previous slide, is a global statement. You want to see the complete sequences and find out how many recombination is there, or actually, rather, how many must there have been. So transforming this into a sort of global statement about how many recombinations there are is quite challenging. And my colleague Yun Song and Rune Lønsø, but also others, has worked a lot on this. There's an algorithm, a dynamical program algorithm that can bring you some of the way. It can actually do it, but it's really quite a killer, and we will actually illustrate it again on this data set, the Kreitman data set. So basically what you have here is, for instance, 9 sequences, and it's these 28 columns long. Assume that you have the minimal history of the sequences up to the I-1st column, conditioned, not in a probabilistic sense, but sort of the last column must be this tree topology. Then if you have that for all possible tree topology relating to this column, well, then you can extend this one step further. So you can say, what is the cheapest history up to this point in terms of the cheapest history that is one column shorter. This is the basic algorithm, the basic ideas in this. Why it's difficult is that there's a terrible number of tree topologies here. If you only took the standard unrooted tree topology, it's quite known that if you have 10 sequences, I forgot how many there are, but in enormous numbers, if you have 20 sequences, you've got to keep track of terrible number of quantities in a given column. And in this situation, it's actually worse, because what you want, this is the number of unrooted trees, this is the number of trees if you also remember the relative rankings of internal nodes and the root, called coalescent topologies, and there's an enormous number of them. For every of them, there is a set of neighbors. Basically, a neighbor to a tree is the tree that you can get by taking one tree and removing a subtree and moving somewhere else, the SPR population. And the size of neighbors depends on what kind of tree topology you have. If you want to solve this problem, basically, I've sketched a recursion here, but we have to find out what kind of tree do we actually have to keep track of here. Naively, one would say whether we want the unrooted tree topology, and just to illustrate this, let's assume that we have a proper tree here and another tree there, and we want to know how many operations does it take to transform this into this one. Well, in case we take the tree topology, unrooted tree topology, it takes 1. It's a question of just checking it. If you suddenly remember the root and take the rooted tree topology of these two, then you need 2 events. If you on top of that also remember the internal ranking of age ordering of the nodes, you actually need 3. And if you remember not only the internal rankings of all these internal nodes, but the exact times, you need 4. And the question is, what do we need of these to be able to make this dynamical programming algorithm work? And the fact is, we need something very close to this. And it's basically the reason why we need this is that recombination, when you take a subtree and move it somewhere else in the tree, it induces a time ranking in the tree. So a recombination will take and cut a sequence in 2, and will find an answer to further back in time. And this sort of use of the word further back in time immediately makes it necessary for you to remember the internal rankings of the tree order. So basically, the bad news is we need this number of trees. You can do different things to accelerate this algorithm. This was done by Yun Song about 3-4 years ago. So it's not totally bad as this, but the limit of this algorithm is about 9-10 sequences. And here we have 9 sequences. So basically, this again the Kreitman data. And this dynamical program scanning algorithm was applied to the data, and we found the minimal number of recombinations necessary for this. And what we have up here is an ancestral recombination graph. So every time we have 2 lines merging is a coalescent event or a duplication event. Every time we have something that is like this, a line is splitting, coming into 2, we have a recombination event. When you take a tree like this, for a given region, or an arc like this, for a given region, there must be an old-fashioned phylogeny. because if you only take a single column of nucleotides, there's not going to be recombination with a nucleotide, but nucleotides will find common ancestors. So any region will have an old-fashioned phylogeny. So inside this ancestral recombination graph, there is going to be a set of phylogenies. Okay, and this is if you now trace the red lines and ignore the gray lines, you're going to find a tree within this one that is described this one. The phylogeny of the relationships of the sequences in this one. If you then switch this specific border, you're going to, instead of following this line, you're going to follow this line. And you're going to switch the tree by actually an SPR operation, because you have taken the subtree hanging from this one, and instead of having it here, you plug it in there. So now you jump to another tree, you jump to another tree, jump to another tree, etc., etc. In total, you will get 7 recombinations like this, and you have a sort of a total minimal history of this. The reason why this has been sort of highlighted in blue is that if you remove this one, you jump from 7 to 5. So one could consider that was a sequencing error, since it has so many consequences for recombination. Okay. So this is basically a totally non-statistical way of taking a data set and finding the minimal history. And there's a very large number of minimal histories. What could ask is how good a guesser is that of recombination events and of local history, and that's basically what's been done here. So the first thing that one could ask is how many recombinations is there in the real history relative to the reconstructed history? Okay, since we basically have, we can do this by simulation, so basically we simulate a set of sequences and then put mutations on it, and we reconstruct a minimal arc, okay? And by doing this many times with different parameters, we will get a real number of recombinations versus a reconstructed number of recombinations. And basically we've done it here for 8 sequences this is the scaled recombination parameter, and it within the human genome correspond to about 4 megabases, and the row would be about 70 here. This is the reconstructed number of recombination events in simulated data on average. And clearly, the more mutations you have, the greater is the potential of finding all the recombinations. All the recombinations, yes. So if we take this parameter and sort of look at how many recombinations did one reconstruct in the data set of this length, corresponding to a bit less than 4 megabases, well, the original Hudson-Kaplan bound would be this number, so it's listed at 12. The Myers-Griffiths bound from 2002 would be this, while Yun's bound would be about 12. So this is the number of reconstructed, minimal number of recombinations in the data set. The bad news from the point of view of this is that you can also in this model calculate what is the expected number of recombinations in the data set, and that actually follows this line. You can see this line goes further up than this line. You can also calculate what is the potentially reconstructible recombination events, and the potentially reconstructible recombination events are the recombination events that actually change the tree topology from between 2 neighboring sites. And that is a nicer line there, but nonetheless, they're much higher than this one. And you can easily calculate that the expected number of recombination events for this is about this number, while you only found 12. So you see you're more than a factor 10 wrong. And the expected number of potentially reconstructed is this number. So you miss a terrible lot. So the point of view of the original program of Hudson and Kaplan of trying to guess the number, observe the number of recombinations, this is not good. And they noted that already back in 1985. But it's an important point. Another thing one can say is how well does it reconstruct the genealogical relationship? And that's actually pretty difficult, because in some sense, you at least have to make some decisions about this, because you will have to compare ancestral recombination graph with ancestral recombination graph. And there's not too much literature or obvious ways of doing this, but there's a lot of ways of comparing tree topologies with tree topologies. So basically, the way that we compare tree arcs is by comparing the tree topologies embedded in the arc. So basically, you can, again, you know the true arc. You have a reconstructed arc, which is the min arc. And then you can basically sort of scan along the sequence and say at a given point, what is the tree at this position and how alike are they? And at any point, we have sort of asked how many bipartitions do they have in common? So if you have 7 sequences, you're going to have 4 bipartitions. And if you have 8 sequences, you're going to have So here is again some simulations, and the news concerning that is considerably better, because if you simulate there, you find out that the percentage of the bipartitions are actually quite good. That basically means that if you put in recombinations, you will put in the recombinations that ensures you to be guessing the correct local tree. You will not put in a lot of them, but you put in the ones that's necessary to reconstruct the local tree. Fine. So this is about 2004 scale situation with this. There's some other fun thing about this graph. Clearly, when you guess a local tree on these sequences, a specific position, well, you are reconstructing the total arc. But at a specific point, the local tree must be related to the neighbor local tree by one SPR operation. So basically, the information you have on this tree is not only in the sequence data there, it's also on the neighboring trees. And when you get to the boundary of this thing, you don't have any information on the outside. So you get a better guess in the middle than on the outside, which is sort of obvious, but it's still a nice little curve that illustrates this effect. About 2004, 2005, Rune and Yun came up with an alternative way of doing this. It's actually surprising that it works so well. And that instead of scanning the sequences, you go back in time. And so basically what you have here is that you have your data set, and that could be the data illustrated in the previous earlier slide. And you know you're going to end up in one single ancestral sequence without mutations on it. And the question is just what is the shortest history back in time? At first look at this, this should not be a very promising approach, which will be shown in a later slide, because the number of configurations that you can meet is enormous. So basically, while the number of tree topologies and coalescent topologies was large, the number of states you could visit when you sort of take this view of going back in time is much larger. But it happens that you can, it just happens to work if you use the right technique. So basically, and the right technique here is branch and bound. So you basically take your data set, and then you define which are the sequences I can get to by one recombination event. And I'm allowed to use any number of mutation events and coalescence events, but one recombination event. The number of sequences I can get to from this data set with 0 recombinations is 3. I hope I'm right. Yes, it is, because of course it's the data set itself. I could remove this mutation, and when I remove this mutation, this sequence is identical to this sequence, so they can find a common ancestor. So that's basically the size of the neighborhood of 3 itself, and 2 sequences you can get to without using recombination. If you allow one recombination, for instance here, this configuration is incompatible, so you must at some point invoke a recombination between these two. If you invoke a recombination, you will get to 91. But clearly, one can define sort of a 1 neighborhood, a 2 neighborhood, a 3 neighborhood. Every time you look at a specific configuration in that neighborhood, you can use one of these bounds, like Simon Myers, another bound, and ask how many more do I need to get to this point. So now I have the length of the small history and a guess of how much more I need. If I have some starting guess of my length of going from this configuration to this one, and that's heuristic techniques of creating a history with the recombinations for a data set. I have 3 examples on the next slide. Then you can discard configurations where this sum plus this sum is higher than your first guess. And it's really efficient. It's tremendously efficient. This is very surprising. Good. So this had 2 components. One is you had a growing set of neighborhoods, and you have a lower bound of what more you need in terms of recombinations. It's still limited on how well it can do. It can do much better than the previous data set, and it's very data dependent because it really depends on the sharpness of these boundaries. But since the data sets that these absolutely can't handle, there has been a series of heuristics where you basically just take your data set and you know you're going to get there, and then you start to apply recombination, coalescent events, and mutations in a rational way to get there in what you hope is a short way as possible from this one to this one. So these heuristics are actually quite useful in defining a first guess on the length from this one to this one. Okay, and there are three there. There's one by Sung and Gusfield and a program called Shrub. Minicello or Durbin had an article where they also used this for mapping in a program called Margarita. Rune has now written a very large program that can handle a very large setup called this quick arc. Okay, I'm going to have a little digression here, basically because the two approaches for solving this was one scanning along the sequences and make a dynamical programming algorithm that came up with a shortest list of local trees. The alternative approach of going back in time would be to go back in time using branch and bound and reconstruct it sort of temporally. And there's a series of algorithms that has this property. There are two versions of the algorithms. I'm going to mention three of them. One is the coalescent recombination. And temporal, this basically means you go back in time. You take your sequence in the present, and then you go backwards in time waiting for events. Okay, in this case, you found a coalescent event. In this case, you found a recombination event. And you go back like this. And you can stochastically describe the rates with which these happen. And an article from Griffiths and Hudson in '83, two distinct articles, describe this process like this. I and Carsten Viuf had an alternative description of this in '99, where you basically start out with a point on the sequences. And then you say, well, on point, you don't have recombination. So you just go back and you have the coalescent process without recombination. So you just sample a tree like this from the coalescent process. And then you sort of remember, I'm not only concerned with the first position, I'm concerned with the whole sequence. So now the process will actually be, I'm going to scan along the sequences and wait for recombinations. And here it is. So basically what you do, you scan along the sequences and ask for how long along the sequences is the first tree that you observed valid. And at some point you find a recombination, and this recombination has not been described within the genealogical structure, and you have to apply the coalescent process to it. So that's an alternative. This is actually quite complicated, while this in some sense is simpler, both conceptually and to program. But this has a different view of it, where you operate on trees instead of operating on sequences. And this thing yields some insights, or at least gives some intuition to the actual process of coalescent recombination. One interesting thing is that if you scan along the sequence, this process is not Markovian. So basically, it's not enough to remember a local tree. You must remember the whole history. The reason why I state this in the next point so explicitly is that this is assumed by HMM methods for reconstructing recombinations, okay? And so it's the next thing as well. The next thing is you're not allowed to reduce the tree to topologies, okay? Basically, if you take a tree like this, you must remember the branch length, okay? Because the length along the sequences until the next recombination is shorter the longer the total branch length is, okay? So it's going to be quite long here, it's going to be quite short there. So you're not allowed to remember, 1 and 2 are siblings, 1 and 2 are siblings. That are not enough to remember it. So both this one and this one is assumed in methods that uses HMMs as a hidden process to reconstruct recombination. It doesn't mean that it's necessarily bad. It can be really good to use these HMMs, but it's just nice to know that these things are actually assumed. Another famous sort of dual set of algorithms is the Elson-Stewart algorithm for temporal peeling in a pedigree, where you observed the data at the leaves, or the individuals in the present, and you know their relationship, and you must sum over the ancestral configurations in the parents and ancestors. So there's an algorithm from '71 who goes backwards in time doing this, and that's really the ancestor of Wilson, Felsenstein 81 algorithm and other proving algorithms. There's an alternative algorithm from '87 where you basically don't go back in time. You take it and scan along the genotypes like this, and then you have an alternative formulation. And the point of this is basically that the process is Markovian as you go back in time, but if you have the right mapping function, it's also Markovian as you scan along the sequences. So that's the second algorithm. And last time I was here giving this talk, I actually made this slide, and I thought I came up with a good idea, and I made somebody who made a good idea. So basically, you can do the same thing for alignment. And basically, what is that? If you do optimization algorithms, the original alignment algorithm was formulated by Sankoff in '73. Well, basically what you do is you take and add a column to a growing length of sequences, and then you formulate a dynamical program algorithm. But you can also do it differently. You can actually align the first two sequences, then these two sequences will create a matrix that you align to a single sequence. And these two sequences here will create a matrix, alignment matrix, and you can then align something that corresponds to a cube to something that corresponds to a square. And one problem that was very obvious to treat in this connection was if you want to find the minimal history of a set of sequences where insertion deletions are longer, as has been stated several times, that was always viewed as a very important step towards realism, but it's hard to do for a complete tree. But this was solved by Bjarne Knudsen in 2003. And in this case, it was much easier to formulate it like this, where you go back in time and merge matrices of increasing dimension, while doing it along the sequences becomes very complicated. I and Dirk Metzler and a lot of other people have worked on statistical alignment, and clearly it would be fun to do statistical alignment. There's been a lot of algorithm who works on it like this, so why not do it like that? So that's why I thought last time I was here. And actually a student worked on it, but as you start looking at it, it's interesting to do this. However, it is not that computationally efficient. It's not much gained. Basically, the reason why one wants to do a thing like this is you have a sequence here, you have a sequence there. And many of the methods of aligning sequences are called progressive alignment, where you basically take a sequence there, and then you create an alignment, which is going to be a string of columns in alignment, and that's one dimensional again. Then you take this alignment and align to a single sequence, and you do like this. Every time you have something that corresponds to strings. And that means that the operation you have to do there is aligning old-fashioned pairwise alignment, and it's L to the squared, where L is the length of the sequence. However, if you want to do what is just suggested on the previous slide, when you have statistical alignment, you're going to have a square and not a string. And when you're here, you're going to have a cube. So as you go back in time, it's going to get bigger and bigger. And basically, the computational gain of doing this temple version is very small, because you basically, here you have to consider something that is 5-dimensional. While if you did progressive old-fashioned alignment, which is going to be suboptimal, you have something that is 2-dimensional. However, it is actually worth doing, but not to the extent that I hoped, because you can get a series of bounds on how much you need to calculate that are stronger by this approach, but it's nothing as much as we hoped originally. I think I can skip this one. And now to the other part of this that is not optimizational, but we want to calculate the probability of a data set. The data set looks like this, okay, just for illustration. And a series of algorithms were formulated by Griffith, Ethier, and Tabaret starting in '87 and until '95 that allows you to calculate the probability of a given data set like this. If you take a data set like this, well, what could happen to it? We still have this infinite site assumption. Well, you can only merge or coalesce things that are identical. So these two could coalesce. You can only remove mutations in individual when they stand as singlets, because the mutation will happen in a single sequence at a time. So what could happen to this one, for instance, you start here and you must get up there. One event you could imagine was that these two merged. One event that could then happen was that, what happened there? That this mutation was removed. One event that happened there was this mutation was then removed, and you go further back in time until you reach this point there. You can, by this kind of reasoning, fill out this complete scheme here. So if you do this, you get this thing. And if you look at this one, clearly there's this event corresponding to coalescent. There's removal of this one corresponding to this one. You can write a recursion that says what's the probability of this one in terms of the probability of these. And that's quite efficient. And you just fill out this table. You know you're going to get to this one. It's going to be probability 1. So you calculate, you fill out a table that has entries corresponding to these configurations. If you take and count how many configurations there are 27 configurations. If you put in recombination in this, first of all, let's put this. If you put in compatibility in this data set, there will be no path from this one to this one. You'll basically find a blind alley. So you can come up with data sets where you can't fill out this one. But if you say, now I'm going to do the same trick, clearly you're keen on finding what's the probability of the data in terms of mutation rate or recombination. So that's nice to be able to do this. But, and you could do the same kind of reasoning allowing for recombination, but you will sort of have in for a bad experience here, because if you put in recombination, the number of states that this one could visit on history back one is suddenly 300 million instead of 27. It's a bit surprising that this, and so you need a bigger slide to do this. But you could sort of, in principle, calculate it. Okay, where is it? This just for illustration, and clearly the goal of the next 6-8 slides is to sort of inch towards being able to do this for recombination. So let's just show a simple case of data. So assume you have a data set like this. So now we have a sequence that happens to be equal to the ancestral sequence, and we have another sequence with 2 mutations on it. The first thing that we're going to assume, and everybody assumes something like this, is that recombination can only happen at the midpoint. So there might be a certain recombination distance between these two, and we turn this into a discrete problem, discrete problem by assuming that all the recombination will happen on this one. I think it's a quite innocent approximation relative to the general difficulty of the problem. How many states could we visit? Well, if we only look at the history of the first mutation or the segment the first mutation on, well, it looks like this. Well, we have to remove the mutation, and then we're going to have 2 identical sequences. 2 identical sequences can find a common ancestor like this. So if we sort of only look at the history like this, we will have to pass through these states. The second part here looks exactly the same. So in the second position, we're going to have the same thing. The question is just how do we combine these? So let's just say we take this one and we combine it with this one. How many ways can do it? Well, at any column in the first position, we must observe this. And any column in the second, for the second mutation, we must observe something like this. And it's simply a question of gluing things together. So you always have something that is from this one and from this one. So you're not allowed to glue things together that doesn't contain anything in your, that comes from this one. You can write a set of recursions. Again, you can do this and start calculating how many ways you can do it. If you fill out the whole thing here, you get 30. So there are 30 ancestral configurations to this one. So histories of this one could pass through these 30 states. Okay, let's just take one simple history through this. So we start out with the data set there corresponding to this one. And you know you're going to get up to a sequence like this. So, but one history could be the first thing that happens is recombination. The second thing that happens is another recombination. Then happens a coalescence event. Then happens a coalescence event. Then we're down to this one. What happened in this history, 2 recombinations and 2 coalescences, is that basically the mutation has swapped branch, swapped sequence. And then you remove one mutation, and you coalesce. That is one possible history of these sequences. And in this case, 30, that's so small that it's not a problem. So you can actually write the recursion. So you could write what the probability of this one in the terms of the ones you can get from. There are several things that are complicating in this case. First of all, you have cycles. You can stay within this component for a long time. So you don't have a directed acyclic graph, but you have cycles. So you have to calculate in this case you have 7 states. You have to calculate a linear equation system. But you can do that in case the components don't get too big. And calculate this one is not difficult. But clearly, as you start to get more complicated data, the number of states grows. So we somehow want to find a graph that contains most of the probability. And there's a very sort of obvious way of doing it. And here's just the graph sort of telling you how many states there are. So this is the 30 that you just saw. Okay. This is it's not 300 million, it's 800 million states for the very simple data set where we filled out a slide when there was no recombination. And this is sort of the largest number we have calculated when this slide was made. And it's basically the number of ancestral states you could visit if you went back in time from this one. So clearly, you don't want to make a graph with all these states. You want to reduce the number in some intelligent way. And that's basically what we tried to do. And basically, we're motivated by this ability to calculate minimal histories. So basically here we have a data set and there's no recombinations in it. So we can postulate histories that goes back to this one and doesn't invoke recombination. And we call that the zero arc. So you could visit this one, you could visit this one. From either this one or this one, you have to go to this one and then this one. So there are basically only two fundamental histories from this one to this one. So that was the zero arc. And the zero arc corresponds of all the states you can visit that steps on configurations using the minimum number of recombinations. The minimum number of recombinations is here 0. So here's the one arc. So if you allow one recombination, you get another 15 states, okay, because you can recombine to this one, recombine to this one. And the moment you use your recombination, you're not allowed to use more recombinations. So this is the number of states with one recombination, and this is the number of states with two recombinations, okay, which is all 30 of them. I should state that the moment that you say, I'm now going to use my recursions and my history by only stepping on these, I actually have defined a set of states that I can reach in one recombination. But the history that steps on these can use more than one recombination, because I can go to this one in a recombination, I can then jump back to this one in a coalescent, back and forth, back and forth, and back and forth. So although this graph is only defined in terms of the minimum recombinations, it will contain cycles, and it will actually contain a much larger set of histories than only histories with one extra recombination. Okay. And basically, here we calculated what is the likelihood of this data set with this parameter, mutation parameter and recombination parameter. Clearly, if there's no recombination, you're not going to invoke any recombination whatsoever. So we're never going to visit the states that needs a recombination. So you're not going to visit these and not going to visit these. So the probability is going to be the same, because all the probability is coming from jumping on the minimal arc. The moment you put in some recombination rate, then you're going to get additional probability of your data by summing over the states that needs one recombination and two recombination. And you can sort of plot things like this. Okay. Just to show you how this thing works for a slightly larger data set. So now we have this data set there. And before going to this, I could sort of ask myself, how large do the index there could it grow to get the full ancestral recombination graph? Well, you have 5 sequences here. And you have a recombination between this position, and this position. They're basically going to be, since there are 3 positions, there are two places between the recombination happen. So basically, if you took 10 recombinations, you could separate any of these mutations on 15 little islands that you could then put back together totally at will. Okay. So that's basically, with a 10 recombination, would allow you to take this configuration and reach any configuration you could conceive of that could be ancestor of this one. So in principle, it's the number of sequences multiplied with the number of segregate site minus 1 to reach any. However, after this, you have the problem. You've got to get back to the ancestral sequence. And this second number is not known. But it's at least less than twice, in this case, 10. So if you had 20 arc, you're going to cover everything. But clearly, you can easily show that you don't need as much as this. So basically, the number of configurations in total here is 400,000 something. And the number of configurations in the zero arc is this. The probability of all possible paths is this. In the zero arc, if you allow one more, you're going to jump up to still have very, very few states. The probability then jump to this. And if you have a 2, you're basically indistinguishable from taking the full arc. Okay. So basically, it just shows that in this case, with these parameters, if you take the 2 arc, it basically contains all the probability mass, and it's vanishing small, still very small compared to the total arc. If you look at the likelihood surface of these, well, here clearly a 0 arc is not good enough, but 1 arc is actually already getting there, and a 2 arc you see something, an extra thing above there, and there's only a slight change in the maximum likelihood estimate. So that's just an illustration that a lot of the probability mass is actually contained within these smaller arcs. Okay, this is, we had a series of investigation of how large numbers, how large arcs we can actually get to. And we can get to 7, 7, which I think is about 21 digit long number. So you can calculate the 1 arc, 0 arc, 1 arc, and 2 arc, which is enough to calculate the probability of this. And the amount of acceleration that you have sort of gotten relative to the complete thing is more than 10 to the 7th. Okay, and so you might say this is not a major achievement, but nonetheless, we managed to find a subgraph within a very large graph where we can say all the probability mass is there. And most other results for this would basically only say something about 2 sites or something like this. So this really allows us to calculate things that are larger than this. It was our wish, and that's the thing we didn't get to, is the moment we have things like this, like 7, 7, we have quite a complex situation that we can analyze in detail. And a lot of these samplers that are out there failed for unknown reason. And it would be very interesting to know, why does these not work as well as people had hoped. There's a series of these out there now. And clearly, the moment you have a situation like this, you can analyze it in great detail. Okay, I might not. I have a couple of ideas that we should do in the future. It'd be nice to have upper bounds and lower bounds. Concerning the heuristic algorithms, like Quark and many of the others, relaxing the infinite site assumption would really be very, very nice, and it's quite doable because it's basically just a question of saying, well, here I have a configuration. I'm now allowed to have 7 mutations at the same position, but I must take an intelligent step towards removing incompatibilities or towards removing the ones that I believe are mutations relative to the ancestral states. So it's just a programming sort of task. And I have 2 more slides, so that are other points relating to this. Last summer, Joanna Davis and František and we had a little project that was motivated by the wish of analyzing very large genome segments. If you use the coalescent process for recombination, it is an assumption in this theory that the sample size is less than the square root of the effective population size. That's something we assume. And the moment you go beyond this, you're making an assumption. And if the sample size is less than the square root of the effective population size, you very often have a discrete model that you then transform into a continuous model, and this transformation is valid. However, if you have a large number of recombinations, recombination, as we saw before, is basically creating a new ancestor. So you can basically just take one chromosomal piece, and out of this, you're going to get more and more ancestors. And at some point, you're going to violate that the number of sequences carrying ancestral material is less than the square root of the effective population size. And we investigated this, and it was actually quite fun. So basically what you see here is the rate of the number of coalescent events rates when you have a discrete model, which is the correct model. This is the continuous approximation, or vice versa, sorry. So you really have a disparity between the rate of coalescent in your model and in the model you assume is correct. So that basically means that you will overestimate the rate of coalescent events relative to the true model. And basically, well, we did a couple of other things. So basically, we took a set of sequences, and this R is the total number of length of the genome in Morgan. So basically, we just assumed we had one chromosome, and then we asked how many ancestral sequences are we going to have in a continuous model, the standard coalescent model, and a discrete model that simulates all the sequence correctly. And clearly, in the discrete model, you're going to have way more ancestral sequences than you have in the continuous. Okay. So there's a major, if you take complete chromosomal pieces, the standard coalescent theory of the recombination doesn't work very well. In some sense, it sounds quite damning, because the moment you do a present sequence complete chromosomes, And clearly, many of the quantities that you estimate are wrong. However, the good news is that quantities such as linguistic equilibrium are correct. And there's an explanation for this. This basically means that these models are globally wrong while they're locally correct. Well, what does that mean? It basically means that if I take these models and only use the coalescent with recombination model for a small segment like this, well, then I don't have a large recombination rate, and I don't get a larger number of ancestors. While if I take it for the whole thing here, I have a large recombination rate, and the number of ancestral sequences that carries material to the present sequence goes to a very large thing. So basically, if you take along any segment like this and ask questions about this, the quantities of interest are correct. While if you do it for the total thing, it's wrong. And basically, why there can be this disparity is basically because segments like this and segments like this are far away will sit on the same sequence with a considerably higher probability than you would expect to according to the standard model. It's quite nice because it basically means that things like any questions evolving locally is actually fine. But if you want to ask a global question like, what is the number of ancestors carrying sequences, you're probably wrong. And the last thing that I've been working on with Mike 2-3 years ago is that clearly the ancestral recombination graph is within individuals. Okay, so it's something that you can embed within a pedigree. Although all these models formulated as if there was no individual, only sequences. Basically, what is the situation? Well, here you've taken an individual. Here you've taken an individual. And you can then trace the sequence material up through this one. So any specific point, there's only one path. So any individual has two parents of different sex. So any individual, any position in the sequence will have a single path up to a common ancestor through this, and you have to choose it like this. It's an open question that Mike and Balchandran has worked on, but it's still an open question that sort of hints toward it. If you know sequences under idealized models, if you know the pedigree. So basically, you could imagine that you had a model like this. You have two sequences, now this one, and you let the recombination rate goes towards infinity until you also let the mutation rate go even faster towards infinity. That will have the consequence that you're going to have infinitely many recombination on a given segment. And what's the consequence of this? The consequence is that basically, if you take a genome here, you're going to get infinitely much from your mother, infinitely much from your father, and that's going to go on further back in time. There's no problem of losing ancestral material, which is typical for coalescent theory. So that's a consequence of let this one being infinity. The consequence of let this one be infinity, that for any segment, however small you take it, that means you could take it so small there's been no recombination in it. You can just look at this segment and compare to the other segment, and you measure the density of recombinations. And then you can say what's the length of the path in this history. Okay, so if you have an idealized model like this, what's the consequence? The consequence is that you can observe all the phylogenies for different positions. Okay, you can't observe the arc, but you can observe all the local phylogenies at different positions. And the question is, do they determine the pedigree? This is a weaker question than if sequences determine the pedigree, because we basically reduced our data to only observing all the local trees. But Mike came up with this counterexample that is sort of interesting. Basically, you have two individuals, and they, of course, have each of them have two parents. But their two sets of parents have only 4 grandparents because they are siblings. So this is a sister-brother pair, and they get these 2 children. And if you ask what is the embedded phylogenies in this one, what's actually the paths up to a common ancestor there, you're going to get this list, simple little list. But you can rearrange this a bit like this. So now you're going to erase this edge, you're going to erase this edge, and you're going to do like this. You're going to basically say, well, there was a case of adultery here. So this man sort of went over there, and that immediately caused another case of adultery there. And if you look at the consequences for the embedded phylogenies, or the sort of distances between the individuals down here, you're going to get the same list. Okay, so basically that's just a simple counterexample that knowing all the distances between positions in the sequences only is not enough to distinguish pedigrees. Clearly, Mike and I got a postdoc to investigate this further, but it's still quite intriguing. Does sequences under standard models, for instance, even very generous assumptions like this, determine the pedigree, yes or no? And people have quite different intuitions about this. And this is a slide about all the things I talked about, in case anybody has questions.
We have time for a few questions.
You talk about ARG up and ARG down. Right?
Yeah, that's just some stray ideas. Okay, do that.
I guess you've got ARG down, right? And it's ARG.
I just say, no, what is that we've done here? Okay, we've basically taken a very big graph and say, can I find a graph within that? Or can I find states within that? So if I consider those states, I have most of the probability. But you could do other things. You could lump states. You can do all sorts of things that might be interesting to do. I think one way of trying to do this might be say, I want to make a statement about the probability within this set of the graph without visiting all of it. I think that's basically what I mean with arc up and arc down. Are there ways of lumping states or doing anything so I can, without visiting, I really don't want to visit all the states for obvious reasons. Can I make a statement about the probability mass in there, up and down? And if I could get something that was close here, that would be good.
You've already got, I thought that the previous slide was showing us.
Yeah, there clearly is arc down.
Yeah, right.
If I take a subgraph, that is one arc down, but you can choose a million arc downs. I can say 0, good arc down.
Well, thank you again.
Okay, thank you.